Guys, so let's get started. So last time we talked about was growth in Dieck's inequality and the Lovász theta function. So as usual, can someone give me a quick reminder about what the main takeaways were? Let me ask first about growth in Dieck's inequality. There was a really neat trick underneath it. Can anyone remind me what it was? Yep.
We've got another side function we want to get rid of, so we turned it into an infinite dimensional vector using it.
Exactly. So the big issue was that when we did hyperplane rounding through Gomez-Williamson, there was the issue that there's actually a nonlinear relationship between how a particular edge contributes to the SDP value versus how it contributes to the expected value of our max cut. That was fine for things like max cut, where we just bounded how far off that linear and nonlinear function could be from each other. But as soon as we talked about things like growth in Dieck's inequality, that was no longer good enough for us. So the main idea was this really clever idea. I don't know how in the world you would come up with it, but the idea was to create a new set of vectors to which you apply hyperplane rounding. You start off with u and v, which actually came from your SDP, the optimal solution in SDP. And lo and behold, you created new vectors, u prime and v prime, that you instead did randomized rounding on. And these new vectors themselves were infinite dimensional, and they came themselves from the Taylor expansion of the sine function. So this was one of the takeaways. Now, can anyone give me a quick rundown of the Lovász theta function? So what should you remember about the theta function?
Between
yes,
the max independent set
yes,
and the max min coloring for the coloring
for the
chromatic
number. Chromatic number for the complement.
Yeah.
Perfect. Exactly. So in fact, what we got was we got an SDP whose value is the Lovász theta function of a graph. And we gave a very short proof that actually the value is always sandwiched in between two parameters that are hard to compute. The max independent set and the chromatic number of the complement of G. And what was remarkable was that there's a natural family of graphs where actually these two things are equal. Those are called perfect graphs. In fact, they're even a little bit more general than that. And that gave you an algorithm for actually finding the largest independent set in a perfect graph. So there are no really simple combinatorial algorithms for that. The simplest things actually come from semi-definite programs. So today, what we're going to study instead, I want to give you a taste of a few different areas about how much further algorithm design is than some of the things we've focused on so far. What I want to do is I want to turn our attention to average case problems. There's one particular problem that I think is a great starting point, is what's called the Clique problem. So I'm going to introduce the Clique problem. And really what we're going to do is we're going to give an algorithm for Clique via random matrix theory. So we're just going to do a brief amount of random matrix theory. I know some of you might be taking entire courses on it this semester, so you guys will help me fill in the details. We'll give an elementary proof of the things we need for Clique. So let me start off by introducing the Clique problem. The first thing I want to do is I want to introduce an even more basic average case model for generating random graphs, which is called the Erdős-Rényi model. So this is the most natural model you can think of for generating a random graph. And I'm going to denote it by g of n 1/2, where here n denotes the number of vertices in our random graph. And here, whatever value I put, here I put a half, sometimes it's called GNP instead. This is just the probability of each edge. And moreover, these probabilities are all independent for each of the edges. So all you do is to generate a graph from the Erdős-Rényi random graph model. You give me a parameter n, that's how many vertices I start off with. And then for every pair of vertices where there might or might not be an edge, all you do is you flip an independent coin, which in this case is 50-50. And if it comes up heads, you put the edge in the graph. If it's tails, you leave it out of the graph. So this is a very simple model for generating random graph. Yeah?
Are we allowing self-edges?
No self-edges. and this is an undirected graph model. So we think about it as an unordered pair ij. So the world's simplest random graph model. Now, planted clique is going to be a slightly different model than this, but the first thing I want to do is I want to think about some basic properties about graphs that are actually generated from this random graph model. So to get us thinking along the lines of what the main theme of today's lecture will be, well, let me ask a basic question about graphs generated from this model. So how large is the largest clique? And of course, what we really care about is, since all graphs could actually be output by this random graph process, what I really care about is, with high probability, what can you say about the statistic, which is the largest clique of a graph that we generate from this random graph model? So this is kind of a precursor to really getting into things like planted clique. But just to answer this question, so can anyone tell me, recalling back to the very beginning of the semester when we talked about a lot of basic probabilistic tools, what might be a good way to try and answer this question? What's the largest clique? Yeah?
One of the approaching it would be to say that to have a clique of size k, you need to have roughly k-squared edges.
Yeah.
Each of them which happens with probability p.
Right.
And this clique can occur among any of the n nodes.
Exactly.
So have some sort of n piece k.
So just to abstract it, what he's saying is that a great way to try and bound, for starters, upper bound the probability of actually having a large clique is just to, for example, look at the expected number of k cliques. And then this is exactly the computation he was doing, that the expected number of k cliques is very easy to write down, is n choose k for all of the possible sets of k vertices that could participate in that k clique, times the probability of actually having a clique on those edges, which is 2 to the minus k choose 2. So this naively will only give us an upper bound, but let's see what this upper bound yields. So in fact, we can now just upper bound this with n to the k times 2 to the minus k choose 2, which I'm going to rewrite slightly is 2 to the k log n minus k minus 1 over 2. So the important thing in this is that actually, if we set k to be just a little bit larger than 2 log n, so we think of delta itself as being a small constant, like 0.01.
By log, you mean log base 2.
Log base 2, yes. Log base 2 for this. Because here what I did was I just took the n and put it in the exponent, so I get it as 2 to the k times log n. Now if I take k to be 2 plus delta times log n, then what this means is that our calculation tells us that the expected number of k cliques behaves roughly like n to the minus delta log n. If I treat this term just like a k over 2, then I'm going to get an aggregate minus delta log n, and I have an extra log n sitting here. It should be delta squared, I think. Oh, sorry. It should be roughly a constant in there, but so let me put a 2 instead. So the important thing is that this now becomes something that's smaller than any polynomial once I get just a little bit above 2 log n. So it actually turns out that in this case, you might be worried that this naive union bound might be really not tight, but it turns out it's not hard to see, and I'll just assert it as a fact. This will be an important fact in our discussion. It's just that in a random graph model, in this Erdos-Rényi random graph model, with high probability, the largest clique, which I'll denote by omega of g, is actually 2 plus or minus little o of 1 times log base 2 of n. So actually, wherever this bound tells us that it's very unlikely to have a clique that's a little bit larger, that's not a deficiency of the method that we're counting the expected number of cliques. That actually is the classic threshold for how large the largest clique would be. So now with this in mind, I can tell you what the main question we're going to study today is what's called the planted clique problem. The question is, what if we take a graph which is generated from the Erdos-Rényi random graph model, and we plant a clique that's much larger than this? Can we actually find it efficiently? So let me explain what the planted clique problem is, and then we'll take a little bit of a digression into random matrix theory after we talk about planted clique first. So here's the planted clique model. And I'm going to denote this random graph model by G, N, 1/2, and K, where K denotes the size of the planted clique. So all you're going to do is you're going to choose some graph H generated from this Erdős-Rényi random graph model that I just described. And what you're going to do now is you're going to choose K vertices uniformly at random, and you're going to plant a clique on them. Meaning that once you choose these K vertices, there's some vertices in this Erdős-Rényi random graph H. So some of them have edges between them, some of them don't. All you're going to do is when you plant a clique on those vertices, you're going to add all the edges which were missing and ensure that those K vertices really are a clique. So in this way, what we get is we get some ultimate graph G. So we chose our random graph H. We chose a random set of K vertices. And then we add in the clique on those vertices. But the question is, you don't actually know where the clique was added. So the whole goal in planted clique is just, can we recover the planted clique? So just as a quick, make sure you guys are paying attention. So what values of K should we expect this problem to be information theoretically solvable?
Above 2 log n.
Exactly, right? As soon as we go to something like
Well, significantly above 2 log n.
3 log n, as soon as we go to something like 3 log n, then what's going to happen is that clique that we planted in here will actually be the uniquely largest planted clique. You need to do a little bit more work to show that none of the other vertices in the graph actually participate in that clique. But it's not hard to show that actually information theoretically, this is a problem which you can find even when the clique you're planting is actually very, very small compared to the number of vertices in the graph. So let me assert what is actually an inefficient algorithm for actually solving this problem. But our main goal today will be beating this algorithm. So what I claim is, and I'm just going to sketch this proof, is that there is a quasi-polynomial time algorithm. So an n to the O of log n time algorithm for planted clique that succeeds whenever, say, k is at least 2 plus delta log n for any fixed delta greater than 0. So I'm not going to be so concerned with getting all the way down to the constant 2, because what we're really going to focus on is what can we do with polynomial time algorithms. That's the main goal for today. And we'll see that we'll be wildly off. We won't get anything with a constant times log n. We won't get anything polylogarithmic. We're going to get something that only finds root n size planted cliques. So there's actually a huge gap between what we know how to do in things like in quasi-polynomial time and end of the log n time versus what we can do with actually poly-time algorithms. Yep.
So just to be clear, this is quasi-polynomial for the maximum for the clique problem.
Yeah, this is quasi-polynomial for actually finding this planted clique, which is planted inside.
Oh, so when you know k, that is.
Yes.
So if you didn't know k,
this will still work even if you don't know k, as long as you have a lower bound on k, that it actually meets this condition. So let me give you a sketch of the idea. So the idea behind this is just that, there's something naive you could try, which you could try looking for all size k cliques in the graph. That might be bad. Can anyone tell me why that would be bad and wouldn't give me a quasi-polytime algorithm? Yep.
It's going to be like n choose k possible.
K might be way too large, right? That'd be really bad. What if we talk about planting like a root n size planted clique? This problem actually gets easier and easier as k gets larger and larger to actually figure out where the planted clique is. We don't want to naively look for a size k clique. So can anyone suggest a fix that's a very simple fix? Yeah.
I usually always look for like a size 2 plus or like 3 log n clique.
Yeah, exactly. That's exactly the idea. So I'm not going to, go into the full details of this, but the idea behind this fact is all you're going to do is you're going to brute force search for a 2 plus delta, or 3 log n, whatever you want, size clique. So even if k is much, much larger than this, all you're going to do is you're going to find a piece of that clique inside just by brute force search, and then what should you do after that?
Remove one and do it again.
You just include everything that's adjacent to it.
Yes, exactly. So the only remaining step in this is what you want to do is you want to find all the common neighbors. So one way that you can think about this, just ignoring this 2 plus delta, what if this clique were like 4 log n? So the idea is that once you're actually looking for like a 4 log n clique and k is much larger than that, once you have those 4 log n nodes that actually belong to the clique, then the only guys who will be adjacent to all of them will be exactly the nodes that should be included in the size k clique to begin with. So I'm only going to sketch this because this isn't the main focus, but the main takeaway here is that this planted clique problem, just by thinking about the statistics of how large the largest clique is in an Erdos-Rényi random graph, it tells us that this is a problem which we really can solve even when k is quite small, as something like 3 log n. Well, it's something that we can solve in quasi-polynomial time, but really I want to ask the question, what can we do in poly time? So one of the reasons also for studying this is a great example of an average case problem where there seems to be a gap between what you can do computationally efficiently and what you can do inefficiently in quasi-polynomial time. So this is the type of problem which actually comes up in a lot of different settings. I can tell you a little bit more later on. But for now, let me instead ask about what about polynomial time? All right, so let me tell you a really simple polynomial time algorithm, which we're going to spend most of today beating. So I'm going to assert what this algorithm can do when it can find planted cliques, and I'm going to give you a hint, and I'm going to ask you guys to help me figure out what this algorithm should do. So what I claim is that there actually is a very simple polytime algorithm that again succeeds. Everything we talk about will only succeed with high probability. But it works as soon as k is at least some large constant times root n log n. So the hint that I'm going to give you, so this is a much, much larger planted clique, right? Because instead of starting with a planted clique that's 3 log n size, it's now roughly root n size. So it's still a vanishing fraction of the nodes in the graph actually participate in the planted clique, but this is almost the limit for what we can do with efficient algorithms. So let me give you guys a hint, and then you guys will tell me how it actually works. So my hint is, look at the degrees. So does anyone have any ideas for something that could work for about planted cliques about root n size? So if I think about the, yeah?
Because isn't that higher than the number of edges we would expect coming out of a random node? No.
Not quite. So let me ask it this way. So if I think about a node which actually belongs to the planted clique or one that doesn't, well, I claim their degree distribution is itself a random variable, which what can you say about those two random variables? So does anyone have any intuition for the difference between those two?
So if it's not on planted clique, it would be n over 2, and if it were, it would be n over 2 plus 3.
Yes, exactly. So let's look at.
That's the expectation.
That's the expectation. So we're really going to care about the deviation, but that's enough of the idea that I can explain this idea in a little bit more detail. So the idea is that actually any vertex u that we care about, what I claim is u's degree itself we should think about as being a random variable. Now that random variable depends on some of the other random variables. After all, it has to connect to other nodes. But what I claim is that in two different cases, we can think about them as being random variables with different expectations. So in the case where u is not in the planted clique, what I claim is that actually his degree distribution is just a binomial random variable, which you take n minus 1 flips of a coin, which are each 50-50, and then you add them up. And that's exactly what his degree distribution is for how he actually connects to his different neighbors. After all, if he's not in the planted clique, then adding those edges within the planted clique doesn't change anything about his degree distribution. So his degree distribution is exactly what it was in the Erdos-Rényi random graph to begin with. Now, let me ask you guys a question. So what should the random variable look like for his degree if u actually belongs to the planted clique? Anyone give me an expression for it? Yep.
So it's c root n log n plus binom n minus 1 minus c root log. Oh, no, n minus c root n.
I don't know if there are root n's in this one. So we're just talking about the random variable, and then we'll get into bounding its deviation for the minute. Let me take who hasn't contributed yet. Yep. Perfect. So we've got k minus 1 because he picks up for sure degrees. He's adjacent to all the other vertices in the planted clique. But now we get this binomial random variable on a smaller number, n minus k, because they're n minus k neighbors. He could be adjacent to. And again, it's a binomial where each thing is a 50-50 coin flip. So does this make sense to everyone?
Yeah, it's the same thing I think you
A
mentioned.
question about wording. When you say with high probability, do you mean that for a fixed graph, if we repeat the algorithm many times, then we'll succeed?
No, as in, that's a great question. Here with high probability means over the realization of that one graph.
So there might be some graphs where algorithms don't work.
Yes,
Okay.
exactly.
But the graph itself has a fixed distribution that we're assuming that the sample from.
Exactly.
Is the Erdos-Rényi.
So the meaning of with high probability is the same as what it means over here, which is when we look at the largest clique, we're not actually repeating this random process of choosing a graph more than once. We're talking about the probability of choosing just one graph out of that distribution. It holds with high probability over the edges in the, the random variables for the edges in the graph that the largest clique will be at most 2 plus delta log n. Yep.
In particular, an easy example where it won't succeed is where there are multiple equally sized cliques, one you planted and one you didn't.
Exactly, exactly. So that's fundamental here because the Erdos-Rényi random graph model can give rise to every single graph. But the important thing is with high probability it gives rise to something which actually you can find, the planted clique. So now what I claim is that with high probability, actually this follows just by the Chernoff bounds. We have that the following holds. So what I claim is that for every u that's not in the planted clique, well, the degree of u, we know that it's a random variable. And in fact, its variance is about root n, because it's actually n minus 1 sums of these random variables. So we know that with high probability, its degree is at most n over 2 plus some constant, let me put it as 4, just to be consistent with this guy right here, times root n log n. So that's exactly where the root n log n comes from. So if you think about this as itself being something like a Gaussian random variable, then its variance itself is n, its standard deviation is root n. So once you go out root log n standard deviations beyond that, it's just extremely unlikely that that random variable was so far from its expectation. So we actually know that this condition holds with high probability over all of the different nodes in the graph, because we can just union bound over them. And what we can do for the matching condition is that we know also with high probability that for every u that's actually in the planted clique, we have that its degree is itself at least, its expectation minus some extra standard deviations for how much it might go below its expectation. So what's nice is that our expectation from this part is just n minus k over 2. And then we get this k minus 1. I'm just going to treat it as a k for simplicity. And then worst case, maybe we go down root log n standard deviations below what our expectation is. So the important thing here is that once this condition holds, now actually the algorithm is immediate. So what's the one sentence statement for how you finish up this algorithm that succeeds in polynomial time? Yeah?
Pick all edges with big degree.
Yeah.
With high degree.
That's all you do, right? So once you have these two conditions, all you're going to do is it tells you your algorithm can just choose all the nodes with high degree. Where this is an explicit cutoff. So for example, every node that actually has degree larger than this is, lo and behold, actually going to belong to the planted clique, and everything that's not in the planted clique won't meet that threshold. So this is a very simple, naive algorithm. For, on the one hand, we had this information theoretic algorithm that ran in quasi-polynomial time that could actually find logarithmic size planted cliques. And now, just by virtue of these few observations and some turnoff bounds, we have a polynomial time algorithm that works with planted cliques of size root n log n, right? So are there any questions about this? Does this make sense? Now, what I can tell you what the main content of today's lecture is going to be, we're going to work a little bit harder to actually remove this log n, and that's actually the limit of what people know. So for this basic problem, the only thing that people know how to actually find in polynomial time are root n size planted cliques, and it's actually a major open question, average case complexity, whether there's anything that actually beats the root n bound. So what I'm going to do is I'm going to develop some tools instead of just naive degree counting. We're instead going to work with matrices, which are themselves random because they're going to come from this random graph model. We're going to show how properties of those random matrices allow us to get down to root n. And then I'm going to give you a little bit of a hint about where else random matrix theory comes up in a lot of other problems like things like the stochastic block model and so on. So let me tell you the main theorem that we're going to prove today. This is due to Alon, Krivolevich, and Sudakov. So what we're going to see today is that there is a polytime algorithm for finding planted cliques, again with high probability over the realization of the graph, that works as soon as k, the size of the clique we're planting, is at least some universal constant times root n. That's actually the very best that people know for this problem. All right, so actually the main tool that we're going to be doing, so now I want to take a little bit of a digression into random matrix theory. So let me tell you a little bit about random matrix theory, what we're going to prove about it, and then we'll actually plug it back in to immediately get this algorithm. So the main tool that we're going to be using is this random matrix theory. Let me tell you, actually, random matrix theory is a huge topic in its own right. Let me tell you the types of matrices that we're going to be working with. So imagine we take some matrix A that itself is an n by n matrix, one row and column for each vertex. In fact, the way that we're going to do this is we're going to make it be a symmetric random matrix whose entries are chosen as, for each entry aij, well, it'll be a random plus minus 1 if we have I less than j, or we're along the diagonal. And otherwise, we're just going to put it equal to whatever it should be in order for it to be symmetric. So this is the world's simplest random matrix. All you're going to do is you're going to look only at the upper triangle, and you're going to populate it with random plus minus ones, and then you're going to make it symmetric by populating the lower triangle in the same way, so that it's consistent. And the real question is, what can we say about random matrices like this? How do things like their operator norm behave? So the main workhorse behind this algorithm for plaintive Clique is actually a bound on what the operator norm matrices like this looks like. So it's actually known that with high probability, the operator norm of A is itself about 2 times root n. We're not going to prove this because actually getting down to the exact right constant is actually quite a pain. So there are tons of very high-powered tools that are actually used within random matrix theory. So things like the moment method, the Stieltjes transform, and so on. So instead what we're going to do is we're going to prove something elementary, but we're going to prove a weaker bound, which is good enough for our purposes. So we'll prove the following weaker bound, that the operator norm of A with high probability is at most c times root n for some universal constant c, and we're going to do so just with some very elementary arguments. Very basic geometry and probability that we've been using all along. So that's the main goal. That's the main technical goal today, is we just want to prove something that's even close to what this classic result is about the operator norms of random matrices. Yeah?
Wait, when you say O of 1, do you specifically mean something that's less than 1?
Yeah.
Oh, that's little O of 1, I see.
So the little o of 1 is times the root n.
Uh-huh.
So in fact, the best bounds that are known are that the operator norm behaves like 2 times root n plus n to the 1/3.
I see.
So you should think of that little o of 1 as just meaning that you're very tightly concentrated around it. So are there any other questions about these theorem statements? Do they make sense? All right. So that's our main technical goal for right now. It's just to prove some type of bound on the operator norm of A. And then what we're going to do, at a high level, is the way that this is going to plug back into things like this algorithm for plaintive Clique is that bounds on the operator norm of random matrices are going to help us control the random parts of our graph where the clique is not planted. So when we can control those parts, we'll be able to spectrally find where the clique actually is planted. So that's the main outline, but this is the workhorse behind it. So let's prove this. This is our main technical goal. It's actually a pretty simple proof. It's not too bad. I'm going to break it down into a few steps. Each of these steps will be pretty basic in its own right. So what I claim is, the first thing we might care about is, let's consider any fixed unit vector. X. What I claim is that actually we can control things like X transpose AX with high probability. That, bounding the operator norm is really saying that when we range over all unit vectors X, that in fact this quantity never becomes too large, and that'll give us a bound on the operator norm. But let's make things simple. Instead of worrying about all of the different directions on the unit sphere, let's start off with one of them. So this quantity right here, I claim, actually is, we can think about it as a random variable, much the same way that we thought about things like the degree distribution for a particular node as being a random variable. So this random variable, I claim, what it behaves like is that its variance itself is, well, don't worry about the factor of 2 in front. So let me explain all of these different terms. So this term, if we think about the variance, so X is now a fixed vector, and all the entries in A are independent, except for the fact that we've enforced symmetry. Now, if we think about just the diagonal entries in A, then each time we're going to get an xi times aii times xi. So we're going to get xi squared times aii. And when we take the variance of that individual random variable, we're we're going to get xi to the fourth times the variance of aii, which we get exactly this quantity right here. So this is going to be the contribution from the diagonals. And similarly, when we look at the off diagonals, let me restrict to the upper triangle instead. We're going to get xi times aij times xj, so that's where the square is. We again have a variance 1 random variable that we're multiplying it by, which are the entries in A. And then we have to count this twice because of these guys. Now the important thing, was there a question?
Yeah, we're not looking at absolute magnitude, right? We're looking at the value.
Yeah, we're just looking at the variance of this random variable. Yeah, inside the magnitude, exactly. Now the important thing is just that what this behaves like then
So the mean is going to be 0, by the way, fairly clearly.
Yeah.
yes, is what you can do is you can check that the variance actually behaves like summation of xi squared, quantity squared. So this is nothing more than 1. So the important thing in all of this is that when we have a unit vector, this inside behaves like a very nice random variable. And at the end of the day, what we care about in this type of theorem is we care about showing that for every x, that x transpose ax is at most something times root n. So the name of the game is that if we have this type of random variable, and we want to show that it behaves like, let's say, c prime times root n, well, the question is, what type of probability should this type of bound hold? So if we want for a fixed vector x, and then we're going to have the union bound over many different vectors, if we know what this random variable inside behaves like, and I just want the very, very loose bound of this quantity is at most roughly root n, what type of probability should this bound hold with? So can anyone give me a function of n? So just to reiterate, right, we have a random variable with variance 1. What's the chance that it goes all the way out here into being root n away? So that's root n standard deviations away from roughly where it should be.
And this random variable is morally Gaussian.
Yes, it's morally Gaussian. So same type of heuristic as before. So I don't want to go through all the messy details of Chernoff. But can anyone ballpark this and tell me what it should be?
You get the minus n?
Yes, perfect. I'll be loose and say that I'll give myself a little extra slack and say that this holds with probability something like 1 minus e to the minus 10n. So the chance of just being that far out, being root n standard deviations away from where you should, well, you should really put the number of standard deviations you're away and put the square of that in the exponent. So it's incredibly, incredibly unlikely that you're this far away. That's the same type of thing that happened here when we were root log n standard deviations away from where we should be, that's what allowed us to say that this holds with high probability. So this is just step 1. It's just that it follows from elementary Chernoff bound, which I'm just designing this as a sketch, but you can check the details yourself, that actually this type of bound for a large enough constant c prime ends up holding with very, very high probability. The chance of failure is actually something that's exponentially small in n. So the main work behind this actual argument of proving this weaker version of theorem 2 actually happens in step 2, which is where we actually start to do interesting things. So step 1 was just something that was some concentration bounds that followed by Chernoff and understanding the variances of the random variables that we care about. But what I claim is, the main question here is how we can go from bounding what it looks like on one fixed vector x in order to say something about all different vectors x. Of course, there are infinitely many such vectors. So the idea, which comes up all over the place, is just to actually create a representative set for the entire sphere. So what we're going to do is we're going to construct the set sigma. I'll tell you later what properties we need of it and how we could go about constructing it. But imagine we take some set sigma of unit vectors. These are designed to be representative vectors that should govern, well, what A looks like on not just the set sigma, but over the entire sphere. So this set sigma, what we want is it's what's called a maximal 1/4 net. So what do I mean by that? Is that it has the following two properties. Well, for starters, every pair of vectors in this set, which are themselves unit vectors, have to be at least somewhat far apart from each other. That when we look at their Euclidean norm, the distance between them is at least 1/4. Now, the other thing that we want is, we want that there are no extra vectors that we could add in to make the set even bigger and still maintain property 1. So this is some kind of constraint about being a roughly uniform set of points over the sphere that covers all the interesting directions. So we also want is that for any vector z in the sphere, that there is some vector x, which is actually 1/4 close to it. So there's some vector in sigma with x minus z, Euclidean distance, being less than 1/4. So this just means that it's maximal in the sense that we couldn't have added the vector z into the set sigma without actually destroying property 1. So what this means morally, and we'll see exactly what we need of this set, is that this set is good enough that when we understand how A behaves on just the set sigma, we'll understand how it behaves on the entire sphere so that we can understand its operator norm. That's the intuition behind it. So what I claim now, to realize step 2, here's what we're going to do. If I let z actually be any unit vector, which actually realizes what A's operator norm is. So it's actually the unit vector which maximizes the magnitude of z transpose A z. And it's actually equal to A's operator norm. So whatever z is actually the optimal choice for this random A. Well, what I claim is that what we can do is we can hope that x acts as a good proxy for z. So whatever x actually is the closest in our set sigma, how x behaves on A will actually be a good proxy for how z behaves. Is there a question? Yeah.
So when you say the operating norm, that's over the set S?
Yes, over the unit sphere.
Okay.
And the n-1 sphere.
Okay.
Yeah. Any other questions? All right, so let's do this. So this is where the punchline is coming. So we're going to let x be as in the set 2, right? In this constraint 2. So when we have some z that actually realizes the operator norm, we're just going to let x be actually the guy that's close, that prevented us from adding z into the set to begin with. And what I claim now is that by the triangle inequality, we're in great shape. Because if we take x transpose A x, I claim that this needs to be at least z transpose z A minus the cross terms. See, what this really comes from, just for intuition's sake, is all you're doing is you're taking z's quadratic form on A, and you're instead expressing it as z minus x plus x times transpose times A times z minus x plus x. And all you're doing is you're collecting different terms. So you're going to, lo and behold, have this term, this entire thing equals z transpose A z. And yet, when you expand this out, you're going to get some cross terms due to x, and then you're going to get cross terms due to all the other pairs. You're pulling those all on the other side, and what this tells you is that x transpose AX can't be too much smaller than z transpose AZ. So can anyone tell me how to actually bound the remaining 3 terms on the right-hand side? So what should I use as my bound for this guy right here? Yep.
1/4 off norm of A.
Yes, exactly. worst case scenario, this thing is as large as the operator norm of A divided by 4. Why? Because this is a vector whose Euclidean norm is at most a quarter, and this is a unit vector. This guy right here, same thing. So lo and behold, we can bound it by the operator norm of A divided by 4. What about this guy right here? Not that I really need to be this tight, but what should this be bounded by?
16.
16? Exactly. So I have been loose with the constants. I don't really care that much about the constants. But the basic idea here is now we can say is that if this operator norm is large, then actually there is some x in the set sigma that witnesses it and is roughly as large within a constant factor. So what it means is that if we want to control the operator norm of z, where we care about how large this can be, over all z's on the unit sphere, it suffices to control it over all x's, which are in this maximal quarter net sigma. So that's exactly why we cared about in step 1 having a bound that held with such overwhelming probability, is because ultimately we need to take a union bound over this set sigma. So does that make sense, how these two pieces are going to fit together? And then I'll finish up the details in a minute. So are there any questions about this? Yep.
Generally, is finding a 1/4 net or arbitrary net easy or hard?
Well, so
That's mostly big.
yeah, I mean, in terms of writing it down, it's already pretty big. So it's exponentially large in n. And that's actually why we needed that bound in step 1 to hold with such overwhelming probability. So it depends on whether you think of something that runs in polynomial in the size of the set as being quick or not, but there are efficient ways to do it. The other thing to emphasize is that nowhere in this argument do we actually need to construct the set sigma. We just need to know that some set sigma exists. So let me pull this all together. Let's combine step 1 and step 2 and see what actually remains to be done. So my claim, so at the end of the day, what we had was we had that X transpose A, just to finish this last line of reasoning. And here I'm not trying to get the tightest constants as possible, I'm trying to keep it simple, is at least 1/4 times the operator norm. So what this implies at the end of the day is this very useful inequality, just reformulating what we know so far. We know that if we care about the probability that the operator norm is, let's say, larger than c times root n, that itself is bounded by the probability that there is some x in the set sigma where X transpose A x is actually pretty big itself, c over 4 times root n. So now at the end of the day, that's exactly what that inequality implied, was that anytime there is a z that certifies the operator norm is large, there is some x that realizes at least 1/4 of that bound. And now, lo and behold, we know that this is, at most, the size of sigma, let's say times e to the minus 10n. So once we set c prime, for example, to be c over 4, then what we really care about now is this one remaining detail about how large is the set sigma, right? So all that remains is to bound the size of sigma to finish the proof. And actually there's one crucial observation in this, which this is the main idea in bounding the size, is that actually if we take the ball around each x in sigma of radius 1/10, then actually all these balls are disjoint. So does everyone agree with that? Why are they disjoint?
1, 2.
Like
Because
the
of,
1/8 balls are actually destroyed, right?
Maximal.
1.
The 1/8 balls are actually
Yeah, so
destroyed.
they're going to be 2 for 1.
Yeah. So it's true for 1/8 in here just because all of the different x's and y's which are in the set sigma are themselves at least a quarter distance in Euclidean distance. So 1/10 is less than 1/8, so this works, right? So this is the key idea. Does anyone have any intuition for how this type of observation might be used to ultimately bound the size of sigma? Yep.
Can you really just compute surface area for like volume?
Volumes, but yes, exactly. So here's the idea. So what I claim is that the final step in this is just, we know that their union is itself contained in a ball that's radius is not much larger than 1. After all, they were all in the unit ball, so then lo and behold, they're all contained in the ball of radius 11/10. And so at the end of the day, what this means is that the set sigma, the size of it is upper bounded by the volume ratio of these two guys. Because otherwise, we couldn't possibly have that the balls were disjoint. So once we have that the balls are disjoint, then we know that every time we add in an element x into the set, it actually has to take up some of the volume, which is available to us in this original ball that everything is contained within. So at the end of the day, what this actually means is that we have a size bound for sigma, which actually is itself exponential in n, but is a smaller exponential in n. So what this means is that the combination of these two inequalities finishes the proof. So that's it. That's the proof that we need from random matrix theory. The main step is, step 1 is something that's very basic. It's just you care about individual x's. The main work is going on within step 2, which is where you actually create a representative set that if you understand how A behaves on all of them, you can extend it to the entire sphere, and then you just finish by simple union bound, using some bound on the number of elements in the set sigma. So that's actually the full proof for the weaker version of theorem 2. Does this make sense? And are there any questions about it? Yep.
Can you explain how you got from the bottom line on the top board to the top line on the bottom board?
Yes. Which is now carefully, there we go. So once we have that each of these operator norms is each of these quantities that we're subtracting off 3 things. They're at most the operator norm of A divided by 4 for each of them. I don't care about that 16. And lo and behold, Z transpose AZ, the absolute value of that, is the operator norm of A by definition. We chose Z to actually be the thing which realizes the operator norm of A. So lo and behold, on this right-hand side, we have the operator norm of A minus a quarter times the operator norm of A, minus another quarter, minus another quarter. And that's what actually implies this overall inequality. It's just directly going from here to here, which then is what implies this probabilistic bound that it suffices to control how A behaves on a quarter net of the sphere. So are there any other questions about this? It's a pretty elementary argument, yep.
So what exactly, I guess I don't understand what a quartered net is.
So it's a set of vectors. So it's some subset of the sphere. It's actually a finite set, which between every pair, their distance at least a quarter, but there's no room to fit in another vector z, which would be distance at least a quarter from all the other guys that are currently in it. So that's the idea, is that at the end of the day, we needed to make sure that sigma was representative. That was part 1. That was the thing that allowed us to say x transpose ax was at least operator norm of A divided by 4. But we also needed the property that the set sigma was not too large. And that's actually handled by property 2, which is what allowed us to actually give an upper bound on its size. So it's those two complementary properties, that there aren't too many vectors, and that they're together representative of the sphere, which actually implies this overall bound. All right, so what I want to do in the time remaining is I want to show you how this actually implies an algorithm for finding planted cliques. So without further ado, let me actually give you the spectral algorithm for finding planted cliques.
This bound that we gave is actually very robust, in the sense that what if you chose different random variables? What if instead the entries in A had the property that a third of them were +1, a third of them were 0, a third of them were -1? All these bounds would still go through because step 1 still works. Similarly, these types of bounds also work even in asymmetric cases. So this doesn't give you the right constant in front of root n, but is a very robust proof technique.
So it's very similar to JL. Like you have the same type of thing happening with JL messages as well.
Yes.
In fact, I think you can actually get that as a consequence of JL.
Yeah, exactly. Exactly. It's the same type of having one sketch, but in any case, let me now tell you what the spectral algorithm is for finding planted cliques. And actually, the intuition behind this is very powerful because it applies not just for finding planted cliques, but all sorts of other random graph problems too. So first, let me focus on planted cliques, and then I'll tell you where else this can apply. This was the algorithm of Alan, Krivlevich, and Sudakov. So here's the idea. We're going to take this graph G that came from our planted clique distribution, and we're going to construct some matrix A in the following way. Aij is going to be equal to +1 along the diagonal. Fine, that's not a big deal. And the more important thing is that it'll be +1 if ij is an edge. And otherwise it'll be equal to -1. But don't worry about the diagonal. All we're doing is it's not quite the adjacency matrix. Every time we have an edge, it's a +1. Every time we're missing an edge, it's a -1, so it's a symmetric matrix. Now the important thing here is what we're going to do at the end of the day is we're going to let U prime be the top eigenvector of A. So we compute the top eigenvectors, and we're going to create a set P, which is designed to be the to pick out some of the elements of the planted clique. So if we let P be the top K coordinate of U prime, the largest coordinates of U prime, then what we're going to do is very similar to what we did when we brute force searched for a 3 log n clique and then extended it to the rest of the graph. The intuition is P is going to contain a large fraction of it will actually be vertices in the clique, and lo and behold, we can extend it to the rest of the clique just by adding in all the U's where U has at least 4/5 K neighbors in the set P. So at the end of the day, our clique, we're going to have this refinement step where we found something which really does very highly agree with the planted clique. But then what we're going to do is we're only going to take in nodes that have tons of neighbors into that set, and that at the end of the day will be our planted clique. The statement is that actually this algorithm works with high probability as soon as the planted clique is at least C times root n. So does this algorithm make sense? We're going to analyze it, and what remains actually by leveraging this random matrix theory down. It's pretty elementary. So let me tell you now what are the two main keys that we care about. So how does the analysis of this really go? Is based on one step that's pretty obvious and one step which is the thing that uses the random matrix theory, and that's what I'll spend most of the rest of the time on. So the analysis of this algorithm really boils down to the following two things. The first is the main lemma, which says that if K is large enough, the size of the planted clique is large enough, then, again, all this holds for sufficiently large constant C. I don't really care about what that constant is. What I claim is that with high probability, C contains at least 4/5 K vertices of the plaintive clique. So what this means is that when we do the final step, when we set C to be all of the U's, which have at least 4/5 times K neighbors into the set C, this lemma implies that we certainly find all the nodes that belong to the plaintive clique. That's immediate from this lemma. The only other thing, which is just a fact that I'll assert, but is very easy to prove by direct argument, is just that with high probability, no vertex, well, let me phrase it this way. Every vertex U that's not in the plaintive clique is itself adjacent to, at most, let's say 4/7, okay, of the vertices in the plaintive clique. So why this finishes everything is just because if we look at any vertex which is not in the plaintive clique, what's an upper bound for the number of nodes that they could be adjacent to in C? Well, worst case, they're adjacent to all of the nodes in all of the neighbors which they have in the plaintive clique actually do show up in C. And then it could be adjacent to all of the other nodes in C that are themselves not in the plaintive clique. But lo and behold, this is less than what our threshold is. So this fact, which is elementary, tells us that no node that's not in the plaintive clique gets added. So the main heart of the proof really is in this lemma. This is where we're going to use the random matrix theory. So let me give you a little bit of intuition for this now. All right. I'll call it a sketch because there is one piece in here that I'm going to slightly punt on, but I'll tell you the main idea behind this, which is what we're going to do is we're going to decompose the matrix A, which we're given as A is itself the sum of two matrices, where we think about, let me assume for simplicity that all the vertices in the plaintive clique are themselves the first K node. All of this argument doesn't really matter if we don't know where it is, but let me just pretend it's there. That way it's easier to draw. So we're going to decompose A as the sum of two matrices, one of which is just the indicator matrix for the plaintive clique. So it picks out all those guys that are plaintive clique. And lo and behold, we're going to decompose the remainder will be some type of error matrix that has all the remaining plus minus 1, except for the things in the first K by K submatrix. So this matrix right here, I'm going to call this matrix E. So what I claim is that it follows from theorem 2 that the operator norm of E, this error matrix, is at most, let's say, 3C times root. Here I'm cheating a little bit, so can anyone tell me where I'm cheating? There's a slight cheat here. Yep.
Those numbers are 0.
Yeah, or another way to put it is that actually if we think about this matrix right here, I could think about bounding its operator norm as the sum of these three operator norms. This matrix is actually not symmetric, but all of the arguments that I gave for the proof of theorem 2 actually do go through in the setting. So really this is where the random matrix theory comes into play, is that this extra matrix E, which we're thinking of as being additive noise, that obfuscates for us where the plaintive clique is, that itself behaves nicely in that its operator norm is not too long. So I'm just going to punt on that issue and assume this part.
Now your matrix E actually is symmetric, so really all you need to deal with is the zeroing out.
So exactly.
It's
So
going to
either,
help you.
yes, yes. But
If you treat it as a separate sub-matrices, those aren't symmetric.
yeah, exactly. Either way, there's a ton of fixes to this. The important thing is just that whatever I gave you for the proof of theorem 2, hopefully convince you that things like this are true and that you know exactly how to prove them. But now what I claim, and I'm going to call this matrix down here M, just for simplicity. So what I claim is that the operator norm of M is actually great. The operator norm of M is actually K, the size of the Plankton Clique, because it's literally just a rank 1 matrix that's easy to figure out what its operator norm is and what its top eigenvector is. And so its top eigenvector is itself 1 over root k on the first k coordinate, and then it has zeros everywhere else on the remaining n minus k coordinates. So now I can tell you the intuition, which is very simple now. Is that if k is, let's give ourselves a lot of room in here, just for simplicity. I don't really care about optimizing the constant. So if k is huge compared to c times root n, then what we know is that the operator norm of A itself should behave about like the operator norm of M. Because it's the sum of this matrix whose operator norm is gigantic compared to a matrix which we spectrally controlled, which is much, much smaller. The idea is that if the operator norm of A is actually very close to the operator norm of M, then it's going to tell you that the eigenvectors themselves are also very close. And we started off with this perfect eigenvector that actually exactly revealed for us where the Plankton Clique was, but the eigenvector of A now, which has operator norm close to M, is still going to reveal where most of the coordinates in the Plankton Clique are. So that's the idea, is that and their top eigenvectors are close. So I mentioned that there's one thing that I am going to punt on, which is this bound on, how that actually translates into the eigenvectors being close. It's actually a very classic thing. So it follows from standard bound, and for those of you who are curious, it's usually called Whedon's theorem, that the form of it is if you take the sine of the angle between u and u prime, that itself, this was the top eigenvector of the matrix M, this is the top eigenvector of the matrix A, that you can bound it based on the operator norm of P compared to the operator norm that you started with. So the way to think about it is that the matrix that we started with, M, has a large gap between its top eigenvector and its second top eigenvector, because it's rank 1 and its top eigenvector is k. So as soon as you have that gap, worst case, you can try and close that gap to try and distort what this top eigenvector is, but there's only so much it can distort it if the operator norm of E is itself small compared to the gap it's trying to close. So what I claim is that, what I'll really take for granted is the statement that what this means is that the inner product between u and u prime, I claim in our setting, we should think of it as being very close to 1. As I increase k and put this huge 800 in front of it, it's really saying that u and u prime have to have a dot product which is close to 1. And let's see why this actually finishes the argument and shows us that P really does recover most of the Plankton Clique. So my claim is that under this type of condition, let me just call it star. So under this condition star, which holds through some bounds for matrix theory, that under star, we know the following. So my claim is that at least 4/5 k of the first k coordinate in u prime has value. I'm not trying to optimize these constants again. At least, let's say, 1/2 root k. So So it started off with an eigenvector which just had one of the root k's everywhere. What I claim is that if u and u prime have a dot product which is at least 0.99, then it really tells us that u prime, its first k coordinate, a large fraction of them actually have to be above 1 over 2 root k. So you can give me some intuition for this? This is a pretty simple one, yep.
If we had both the things of one of the two k's, it decrease the dot product size.
Exactly. Every time, let's say instead we had 1/5 times k of the first coordinate at value less than 1 over 2 root k, then lo and behold, that's a huge amount of loss that we haven't picked up for the inner product that would prevent us from ever getting up to 1 minus 1 over 100. Now the same type of thing, this tells us that many of the candidates, the first k coordinates in u prime, actually are large and would be candidates to add to the set T. So what do we prove to complement this? Does anyone have any intuition? What's the remaining step that we need?
The rest of it, right?
Yeah, exactly. We want to say that at most 1/5 k of the last n minus k coordinate of u prime have values at least, let's use the same threshold, 1 over 2 root k. So the idea is that if a ton of coordinates actually had a large value off of this set out here, then what that means is that's actually an orthogonal direction, a direction that's orthogonal to u, that we have too much mass. And then just by Cauchy-Schwarz, there's no chance that actually our inner product could be large. That's because when we project u prime and remove all these other coordinates where u is 0, we just don't have enough mass left over in u prime. So this is not an attempt to optimize these constants. These constants do work. But what this means is that at the end of the day, the final punchline is that among the k largest coordinates in u prime, we know that at least 4/5 k of them are itself from the planted Clique. And that finishes the proof of the main lemma. So that's exactly how random matrix theory comes up in here. In fact, what's really going on is actually a more fundamental thing that comes up all over the place. Okay? So here, what was the mechanism by which we used random matrix theory? Was we thought of the actual planted piece that we want to recover in the graph as itself being some rank 1 matrix that's partially obfuscated by the extra noise due to our sampling procedure of which edges are in and which edges are out. And so what we did was we used random matrix theory to bound the error to say that what we're given is actually close to the idealized thing without the noise. What I claim, and I'm briefly going to sketch this, is that once you have these tools like random matrix theory, there are a lot more settings where you can actually think about applying them. So I'm going to give you one more quick example of how exactly random matrix theory comes up in algorithm design is for something called the planted bisection problem. So it's another random graph model, which is going to fit exactly into this framework as well. So let's imagine that we instead created a random graph which on n vertices has some hidden bisection with different connection probabilities. So imagine that the graph is somehow cut up into n over 2 nodes and n over 2 nodes, and then P represents the inter-connection probabilities within each cluster, and Q then represents the intra-connection probabilities between each pair. So this is a slightly fancier random graph model, which is defined by two parameters, P and Q. But the idea is that if we think about Q as being less than P, it's something where we're planting the fact that there's a pretty good bisection of the graph right here. So the idea now is that, a theorem which we're not going to prove, but I'll just assert due to McSherry, which also uses this idea of random matrix theory and spectral partitioning, is that there is a polytime algorithm to recover the true partition, the true bisection, actually, which succeeds whenever P minus Q over P is at least P log n over Pn. So you can think about this problem as you get a larger and larger gap between P and Q, as you have more and more probability of connecting edges inside, then all of a sudden the fact that there actually is a hidden bisection at some point starts staring you in the face. So it's not so important exactly what these are. Well, let me state the intuition, which is the idea behind this is actually the same exact thing. Is imagine we take a matrix A, which in our case would be something like the adjacency matrix. So we take our graph G, which came from the random graph model, and the idea is that what we're going to do is we're itself going to decompose this adjacency matrix as the sum of two different matrices plus some error. Okay? Because what is the piece that's actually planted in here is this average graph, which itself has connection probability P within a community, connection probability Q across it, and then is obfuscated by some extra error that actually comes from the random process generating the graph.
This is just expectation plus deviation.
Exactly. This is expectation plus deviation. So with this as the intuition, can anyone tell me what might be a good algorithm? Let's say you were in this slanted bisection model, and you wanted to try and find the bisection using spectral properties of the adjacency matrix of A. Can anyone use this intuition to actually tell me what the algorithm should be? It's actually very intuitive. So for the planted Clique problem, I took the top eigenvector. What should I do here? I'll give you a hint, more than one eigenvector. Not quite top P. How about top 2? So the idea is that this expectation matrix P, Q, Q, P is itself a rank 2. Yep?
Because P, Q, plus Q.
Yeah.
And that is P, and then matrix.
Yeah, exactly. So the idea is that actually this piece right here, you can think about it, it's actually a rank 2 matrix. So you're hoping that the adjacency matrix you're given is some rank 2 matrix where the top 2 eigenvectors are quite large, plus some random matrix A whose operator norm is hopefully much smaller than that.
I think rank 2, not rank 2.
It's rank 2, although sometimes you have to ignore the top eigenvalue. So let me ignore that for the time being and just end with the punchline that what you're going to do for a lot of these things is the same idea of actually taking the expectation plus the deviation, this idealized piece plus the error. The fact that you can bound the operator norms of this error is what gives you algorithms for these problems. So this gives you a lot of average case problems are based on ideas like this. So I'll end there. What I'm going to do next time is I'm going to do compressed sensing. So I'm going to continue my sort of tour of a few different areas to give you a sense of where else algorithm design fits in beyond some of the classic topics.